So during this lecture 3.5, we will be speaking about the superposition principle, which is extremely important, not just on this course, but in optics and photonics in general, and also basically in every branches of physics that I can imagine. Superposition principle is extremely important. So please keep your attention during this lecture that we are dealing with next. So I will be going through first a case of a superposition of two waves, and I will be showing to you that just saying that the differentiation is a linear mathematical operation, and this has given implication. Basically, it gives us a rise for the superposition principle, and then I will show to you that also the resultant wave that comes up when we sum two waves together or many waves together, this wave also fulfills the wave equation, and this is super nice because then it has a lot of implications for the superposition principle or formation of this principle. Then I will, say a little bit about the fact that light doesn't really strongly interact with light. So unlike with electrons, photons don't really see other photons that much. So most of the time we can just happily imagine that photons travel without seeing other photons, and this is like a very different from the case when we have electrons inside a solid piece of a material. Electrons are fermions, and they also have a mass, and also the material system is totally different. So the kind of physics of waves is quite different when we are looking at photons and electrons, for example. And subsequently, when we are calculating, for example, superposition of waves, this most of the time is adequate so that we do not need to consider about the interaction of light with itself or with other components of light that are present inside the medium. And then I will finally speak about the constructive interference, destructive interference, so that we can kind of understand what are the ramming implications of superposition principle. So this is what we will be covering next. So, like I promised, I will start by just going and summing two waves together. So let's consider two waves, psi1 and psi2. And we know that they are waves, so of course independently they should fulfill the wave equation. So basically mathematically put, we know that psi1 must fulfill this differential equation. V is the speed of this wave inside the medium, and then since the psi2, the second wave also fulfills the wave equation since it's a wave, so we have a similar equation. And because the differentiation is a linear operation, the psi1 and psi2, we can just multiply them with a constant factors, a alpha and beta, and we can still form a superposition wave. So resultant wave or sum wave or superposition wave, psi sum, we can always form this kind of wave that will be of form alpha times just a constant times the psi1 time plus beta times psi2. And since differentiation is a linear operator, we right away know that this resultant wave, this superposition wave, this summed wave, also fulfills the wave equation. So mathematically, this of course means that we can form a similar looking wave equation, but now we just plug in psi sum instead of just psi 1 or 2. And this is what we get out. It doesn't look much, but this is actually very important. And the kind of why it's very important, there's two very strong implications that arise from this piece of mathematics. So when we think of disturbances, and disturbances can be think of as kind of being sums of many harmonic waves, we now see that we can either think and understand these disturbances and how they propagate. Like we can either look independently of each of those plane wave components, and we can look how the plane wave components propagate, and this gives us then the kind of evolution of the total wave. And why this works is that in a linear system, light doesn't really strongly interact with light. so that the resultant wave can be really thought to be a kind of superposition of all the wave components it is made of, all the harmonic wave components it is made of. And this is very important. So we can have a more arbitrary looking wave, and we can just decompose it into plane wave components, harmonic wave components, and we can look into how these different components propagate. And once we have solved that, we can then put the different components together, we can sum things up, and then we know how the disturbance, the more arbitrary looking wave, has been propagating. Another thing that we can do is that then, like when we are looking at the total disturbance or wave in a given position and in a given time, we can simply just calculate this always as a superposition. And in our case, we were summing two waves, so we can always just like sum two waves up. But of course, this generalizes into 3 waves, 4 waves, n waves, quite a many waves. And we can still do this piece of mathematics quite easily, especially with computers. So this is the power of superposition principle. And it really arises from the fact that this is the important thing here. Differentiation is a linear operation, so that we can plug in many waves inside the wave equation. And this fact that light doesn't really strongly interact with light. So most of the time we're dealing with linear optics, and we don't need to deal with nonlinear optics. And then superposition principle holds exactly. And then we can calculate things and understand things very easily. And now let's go through the concept of interference and constructive interference and destructive interference. So when we are calculating the superposition of waves, what of course is the most important thing is that what is the relative phase between these two waves. And this relative phase entirely dictates the outcome when we are summing these waves together. So if the phases have the same, they are in the same phase, then we are speaking of in-phase addition. So if waves of psi1 and psi2, if they have the relative phase difference of 0, then they are in same phase, so we speak of in-phase components. And of course, in this case, the two waves strengthen each other up, and we speak of constructive interference. And this is highlighted in the A figure here, so that the amplitudes get amplified in the locations. When we are dealing with these locations of the wave here, when we are at the 0 location, nothing changes. But in these, of course, we have constructive interference. And then if the phase difference is 180 degrees, we say that the waves are exactly out of phase. And then this results, the waves get weakened up, and we speak of destructive interference. And the resultant wave here, the solid lines in both of these figures, we see that this is actually now the resultant figure is actually a wave that is smaller in amplitude than the individual wave components, because we have exactly opposite phases, as we can see in this case. And in this case, when we have constructive interference, psi1 and psi2 have amplitudes of this roughly, and then the resultant wave, psi here, it has a way larger amplitude. So this is how we can understand interference effects. So we apply superposition principle, we sum up waves, and depending on their relative phases, either they add up or they don't add up, or something in between. But this is the mathematics that gives us interference effects. So that was it. This was my lecture this time. And next, I will generalize in the next lecture our description from the sines and cosines into the complex representation of waves. So thanks and bye-bye.